What was it? Was it? This is handmade, guys. All right, so I'm Thomas. I'm from Resonate, and essentially what we do is we build speech-to-text models that are customizable very easily. At least that was what we try to promise, and we try to deliver on. And today I'll be speaking very briefly about how we think about speech models, specifically speech-to-text, and how you can customize them. I do like to apologize because it seems like this is a bit of a technical presentation, so I do apologize for that. So why customize speech-to-text models? Last day, I was at a billing company, and we use them for billing, and the name was Solvimon. And during the meeting, we had the transcription running, and you see that the name Solvimon doesn't quite get recognized accurately. In my previous company, we used to do healthcare, conversations between patients and doctors, and there you would see that medication names were mistranscribed quite frequently. As a result, if you miss these transcripts, you're going to have very catastrophic downstream issues. So how do you customize speech-to-text models? I think there's 3 ways you could do it. One way is the most painful way you could do, which is fine-tuning a speech-to-text model. I think I've seen it as a lot. People try it initially, they collect some data, they fine-tune their model, they tell me it's better than you, and then what you see is that it does really well within that domain they fine-tune on, but then the moment they are using it in another location, like say we were to record audio inside a hospital, and then we would go back to a general practice with a different room, different acoustics, the model just catastrophically fails. Now, another thing I see people do these days is, okay, you know what? Like many problems in life, we just slap some large language model on top. So what happens, we have our transcript, and we ask a large language model, please just correct the transcript. So, for example, here we have the medication issue, and we have this hint like, hey, maybe I transcribed something that looks like a medication name. And sometimes the large language model does a really good job at recovering the errors. Sometimes not so much, and sometimes it just comes up with results that don't really exist. But before I want to dive deep into how we do it at Resonate, I want to take a bit of a step back and talk about speech models in general. So I think it's a bit underappreciated that we use speech-to-text daily, frequently, but we don't really know what's under the hood. So I'd like to do a bit of a detour. So speech models are made of, or generally made of, an encoder and a decoder. So the encoder encodes what is said. It encodes what it hears. They are the ears. And a decoder is more of a brain that tries to make sense of what was said. And even today, we still don't really know what is best. And I think that's fascinating. So Whisper was one of the more groundbreaking models in speech-to-text history, at least for me. And Whisper took the approach, you know what, we have pretty good ears, and we've got a pretty big brain. And the combination of the two should have a very nice balance. So I hear well, and I think well. But as a result, you get a bit of a pretty hefty, big model. And generally, we don't really see Whisper used in production as often, because it is a bit chunky, it's a bit big. Then NVIDIA came around, was like, you know what, we're going to have very big ears, like massive ears, but we don't even think what was said. So then Parakeet came along, and Parakeet to this day is used quite frequently. So keep in mind, it has a very tiny brain, and that can sometimes cause them to be very acoustically good, right? They can transcribe exactly what was said very well, but the moment you have medication names, Parakeet tends to come up with their own ways of spelling the same medication name. And then, of course, large language models came around, and then we will have like a tiny encoder and a massive brain. And what turns out, these massive brains are really good at almost getting it right. So what happens is that you hear pretty okay, but you think so deeply what could have been said that you tend to be correct a lot. And I just love this. I mean, Voxra also came along, which is a bit of the same, but I love this because it's such a wild world of like, okay, what do we go for? What works best is that we don't really know what is best. So here you'll see Whisper, interestingly, although it's a pretty old model, still be pretty competitive. parakeet also being pretty good, and the LLMs also being good. So I can't really pick a winner based on benchmarks anymore. I don't know what is best. And that leads us to kind of think, okay, so given we have these very good models, then how can we make them very good at specific use cases? Is a bigger brain better than better ears? And also a bit of a more like nerdy thing, I also believe that we're not there yet at all when it comes to encoders. So we've been trying different encoding architectures, and the purple one is current state of the art. And if you just read at least 5 of the latest papers on any LLM training, and you just apply the same principles to encoder pre-training, you'll see that you can get to state of the art really quickly, just on encoder level. But that's a nerdy tidbit you can ask me later. So how do you customize speech models? So we have our little speech model. And one of the prime ways Whisper initially, so OpenAI introduces, is, okay, you have a prompt. And we all know prompts now, but back then prompts were quite new. So what we could do, hey, this is a piece of audio, please transcribe it given this context. And this worked pretty well, but it's very limited, right? It can only describe a few words. It does it pretty well, but at the same time, it doesn't scale well. Then a bit later, hot words came along. So suddenly, instead of having a short prompt, I have a massive list of words that I want to bias for. So instead of having, let's say, 5 words, I can now support up to 1,000 words. And this worked pretty well. Then, if we go back a bit in time, we would have these things called phrase boosting. And it's getting a bit more used to these days. And whenever your ears are really small, this prompt approach doesn't really work well. So you have to find ways to make the brain a bit smarter, and this is essentially the way they do it now. And if we go really way back in I think 2000, well, less than 2010, we wouldn't even have a tokenizer. We would just have, okay, this is my dictionary, and you can only use these words in a dictionary. And basically, this is also an approach that's still used today. And actually, in healthcare, it's a very common approach in speech to text, where you've got a very big ear, and you've got a nice little dictionary. And in this dictionary, these are all the words you're allowed to transcribe. You're not allowed to move away from this dictionary. Actually, this is what my previous company, Juvely, only used. So we constrained the words we were allowed to transcribe to a fixed amount of words. And this actually did massively well for healthcare, because we couldn't really mistranscribe medical terms anymore. And for us, this was a really nice way of doing medical terms really well. And then there's actual language adaptation. So there's, say you have thousands of words, you could actually train a tiny little model on top of your dumb model to then have, during decoding, really assist you basically grow your brain. So a bigger brain with bigger ears. Now, where it gets really difficult, especially for context biasing, is, okay, say I have 200 medication words, and I want to scale it all the way up to 200,000 medication words. This is where things get really difficult. So how do I suddenly start picking these medication words out of this 200,000 words to maybe 20 or 40 words? Because 200,000 words is way too much. If I use a large language model right now, and I put all my words in the context, then there's a big chance that's not going to work. So a lot of research has been done on, okay, how can we make sure that we can still support 200,000 words in my context and slow them down to maybe 40 in context. And actually, this is where a lot of research is being done now to increase this recall. And then we started benchmarking this, and you kind of realize that although customization is really important, what is also really important is just having a very good model. So here you'll see the word error rate, so lower is better. And you'll see that even though you could have very different models, or you could really try your best in using different architectures, you'll realize that just taking the state-of-the-art best model out there will beat all your work, sadly. So the conclusion for us, okay, we really have to make something that's compatible with these large models, and then during decoding, we'll make sure that the biasing works correctly. And that's kind of my presentation about context biasing. I'm more than happy to take questions. So yeah, please, shoot.
Wait for the mic. And this hand was first, sorry about this.
Go short question, short
short. I'll try. A couple of years ago, I did a couple of things with Whisper. What we tended to do is, because Whisper had a very short prompt context, I thought it was about 200 words when we were doing it. So
Yeah, correct.
So we would pick like the name of the person that was being done and the medications they were on and whatnot. So that was always the most likely thing. And then another one that I did was with radios and radio program transcripts to other things. And then we'd use like named entity recognition, because that's the most likely thing to go wrong. And then we'd have the people that actually edit those things. Are there many other ways where you can see where you can bring in external current AI tools or mechanical algorithmic tools to improve this? Because if we're just doing it on its own, I think we're missing out on all these other things that have existed for years to help us become more accurate.
Yeah, so what you actually see is that now the trend is to train models that predict what wasn't said, but what could have been said. So so this is what we do at Resonate. We train models to not predict what was said, we predict what could have been said. And then based on that, we would know which ones to put in the Whisper prompt in this case. So that's kind of our approach to this, and that tends to work really well, if that makes sense.
Thanks for the presentation. My question, is it these numbers more relevant to the post-processing or like streaming data? Or maybe you can give some insights about the streaming.
Yeah, so there's no streaming. This is all offline. This is all batched. Yes, yes.
Does Resonate do something with streaming, or like you specialize on?
Yeah, I was not allowed to make it very commercial, I'm afraid.
Okay, let's discuss.
I can tell you Resonate has great models, yeah.
I love when my speakers claim something like this on stage. Thank you very much, because that's a reality, right? Another question, maybe? We have time? How much time do we have on
2 minutes and
2 minutes?
45
Okay.
seconds.
No? So do you want to say something commercial then?
It's all going according to plan. Do a weird technical thing and then you get enough time. Okay. No, so we're Resonate. We've been around for 4 months now in Amsterdam. Essentially what we do is we train speech-to-text models and also text-to-speech models. We really believe in training newer novel architectures. So we buy the compute, so we don't actually rent compute. We own one of the larger privately owned compute clusters in the Netherlands. And here we train these foundational speech models that are both good at speech-to-text, but also on this context biasing bit. So we put a lot of effort into promptable ASR. So soon we will go live with an endpoint where you can say, this is a conversation between a patient and a doctor. And from there on out, we will be able to do the correct transcripts for medication, for the context. So we're really trying to get the context biasing right from a large language model perspective.